Hello, everyone, and thank you for joining us today for a LabLinks event titled Batteries Designing a Safe and Sustainable Future. I'm Andy Wadsworth, an editor at Joule, and joining me is one of my co-organizers and co-moderators for today's event, Shanshan Jiang, who's an editor at One Earth. Cell Press is celebrating its 50th anniversary this year and has always promoted science that inspires. We're very proud of Joule, One Earth, and the wider company's role as leaders in championing research in energy and sustainability, and we're certain that today's LabLinks event will contribute further to an important topic that bridges these areas. Developing clean energy technologies and environmentally sustainable processes is now widely accepted to be vital to address the global issues of the 21st century. Batteries represent the most popular class of energy storage technologies and are a vital component in the modern world. However, there are a range of open questions that exist regarding their long-term sustainability, particularly in an increasingly electrified world. Material criticality and rising e-waste are known problems in the battery community, and there are a range of opportunities that academic and industrial teams are exploring to overcome them. In today's event, we're going to cover a range of important topics, including the design of more sustainable battery chemistries, the impact of manufacturing, the use of artificial intelligence for smart battery design, in addition to battery recycling and supply chain considerations. We have a really exciting lineup of speakers today who will discuss these various lines of inquiry with a view towards more sustainable batteries in the future. Before we get started with the talks, we have a few practical points. We'll kick off with a plenary talk from Professor Magda Titirici, followed by two sessions. The first session, Upstream Design and Manufacturing, will be moderated by myself. We'll then have an approximately 30-minute break before we get underway with the second session, Downstream Decommissioning and Circularity, which will be moderated by my colleague Shanshan. Each session will have 4 presentations that last approximately 15 minutes each. And at the end of each session, we'll have a panel discussion with contributing speakers to further expand on the opportunities to make battery technologies more sustainable. Before we begin, we'd like to thank all of our speakers for making time to join us today. And we also want to thank all of the attendees who have joined us to learn more about sustainable batteries. So with that, I'll introduce our plenary speaker today. Giving our plenary presentation will be Professor Magda Titirici, who is the Chair of Sustainable Energy Materials at Imperial College London. She received her PhD in Materials Chemistry from the University of Dortmund before joining the Max Planck Institute of Colloids and Interfaces as a postdoctoral fellow and later became a group leader. Magda received her habilitation in 2013 from the University of Potsdam and the Max Planck Institute before moving to Queen Mary University of London as a reader in materials science. In 2019, Magda moved to Imperial College London to take up the chair in Sustainable Energy Materials. Without further ado, Magda, please take it away.
Thank you so much, Andrew, for the presentation. And thank you all who has joined online for this event just after lunch. I hope you're seeing my screen. My computer says you can, so I hope that's the case. It is my great pleasure to open this very nice session on sustainable batteries organized by One Earth and Joule to talk a little bit about sustainable batteries. And I thought I will start with an overview of what I think sustainable batteries are. And you will see this is an intrinsically complex subject and requires a lot of interdisciplinary expertise to be addressed. So, of course, there is no surprise, I guess, to anyone here that batteries are key for decarbonizing across the sectors, our economy, and to help us transition to a better, cleaner future with no emissions. And because of this, there will be, of course, an increased demand for battery manufacturing. So it is predicted that by 2030, we would need about over 2,600 gigawatts of storage, which is quite a significant increase to where we are now. And as you could see in this graph, which I readapted from the World Economic Forum, most of this battery manufacturing will be for electric mobility, but that's because it's a much, much larger scale, but some also for energy storage. And there's a distribution a little bit by country, and you would see that China will still dominate. China is very big followed by the European Union and the United States. And so the question is, with this increasing demand in batteries, how can we address this holy grail of balancing performance, sustainability, and low cost in batteries? Is it a secret formula? What can we do? And I think before trying to define what a sustainable battery is, which is a very hard thing to do, I think we need to remind ourselves what sustainable development means. And so the definition of sustainable development is meeting the needs of the present without compromising the ability of future generations to meet their own needs. So if we try to translate this to a battery, I would say, and that's just my own opinion, that a sustainable battery technologies must ensure that projection on resource exploitation is done with a safeguard for a healthy ecosystem to support both human and non-human life. And so together with my research group, we thought very much about what are sustainable batteries, and in particular, because I also work in green chemistry, and I like these 12 principles of green chemistry. We thought, can we actually define these 12 principles inspired by green chemistry for green battery or green batteries? And so clearly you'll see here in the bottom that in order to move towards the green battery of the future, we have now, and now everyone is worried about performance, and that is the primary driving force. We need better performing batteries to address our ever increasingly needs, and safety, of course, because we want batteries not to explode, and we want to be able to transport them, store them. I think the next in line, which kind of overlaps a little bit with now, is materials diversification and how we can actually have more local supplies. And while people are already thinking about battery sustainability, I think it's not a must at the moment in industry, but I think with more pressure on legislation, this is going to become a must. So the future batteries will not only have to be performant and safe, and of different chemistries, and ideally as much as possible developed with local resources, but they will also have to be sustainable. Now, what is sustainability? And I guess if you look at this graph, you would see that we've made it a little bit so that it matches with the green battery. So we came up with the first principle, which is green logistics, which means that we need local and low carbon distribution pathways, and we need low cost barriers. The second of our principle is to respect life, which means that we need to really protect the ecosystems. We need to protect the resource biodiversity and habitats. And you would think immediately that this refers to mining of the raw material. The third principle is ensure safety, which means that we need to avoid toxic hazardous materials, and we need to design for a safe operation across all life cycle stages. The fourth principle is efficiency optimization. We need to think of a battery of a whole system, from energy to resources to economics, time efficiency, mass and space. The fifth principle we came with is net zero carbon energy, meaning that we need to use renewable energy source sustainable to drive and charge these batteries. Six is benign processes, manage, use, manufacturing, and disposal in an environmentally friendly manner. 7 would be to be based on abundant material and avoid the use of scarce material. 8 principle would be targeted use, deploy the most sustainable battery types for each application, diversify the battery chemistry, in other words. 9 is tactical design, which means that we need to design these batteries better. We need to manufacture them better. We need to design for disassembling and change a little bit the rigid structures that are in manufacturing today. The 10 principle is enhanced service life, which means design for maximum energy density and for an extended service life. The 11th principle would be to recover resources. So we need to recover everything, materials, components, packs. And the 12th principle will be a yardstick, which means that we really need to standardize battery chemistries and design across academia, but also ideally across industry, and just in general do better. So with that in mind, creating more sustainable batteries is all about looking across a battery life cycle. And in order to come with the definition of sustainability, we thought that we need to look across all these life cycles and define a total sustainability for each of these life cycles. So, you know, in a battery, we go from mining, where we extract resources from the environment. And there we have an S for sustainability. And we need to be aware, of course, on environment destruction, socioeconomic inequalities that are created by mining, human rights violation, geopolitical conflicts, the concentration of war, and also that we might deplete their resources. And so all this S, that it's only to do with mining, you will see that is very complex. And we need to have a plus pretty much in all these categories to create some sort of sustainable mining. And I'm not sure if that's an utopia or not, but these are the factors we need to consider. And then once we mine these materials, we then need to refine them into the final elements or components that go into a battery. And so by refining, of course, we need to redefine another S factor, which is related to water energy uses, byproducts, waste generation, element concentration, and what happens with the residues, where do we put it, what is the geopolitical concentration of these refiners. Once we refine the materials, we start the battery production. And so this is the manufacturing of batteries, which is more taking these materials that were refined, making them into electrodes and making them into cells. And we need to think here for the production, how do we manufacture them? What energetics do we use? Transportation, of course, and distribution logistics between the way where the batteries are manufactured and used. And so we're coming to the use phase here. And for batteries, the use phase is the first life use, but ideally also the second life use. And what we want to avoid is this red thing here, where we put the batteries and store them in a deposit, or even worse, in a landfill. Now, if we want to think how we can make life use more sustainable, we need to think of long-term performance. We need to think of state of health, diagnostics, and safety. And ideally, we want to make sure that we maximize the second life use, and we want to avoid hotspot accumulation, leaching, and we want to avoid no accountability for your product at the end of the life. And so, of course, after that, we need to think of a circular battery economy, and we need to think about recycling, which has an S itself. How much can we recover? What can we recover? What is the purity of the recovering? How much energy did we spend on the recycling process? Did we spend more than even the mining, refining, and production? That's not good. What type of recycling process we use? So as you see, sustainability, as I said, of batteries, because there's so many life stages and they are so complex, is a very complicated issue. So we define sustainability as the sustainability of all these different life cycles over the lifetime of a battery. So now let's go one by one within this sustainable battery chains. And of course, one thing is materials extraction and refinement, which is the first thing we need to think. And here, of course, we have very strong list of critical materials which get updated every year. So the EU updated it last in 2023, and so did US. And if you see the EU and US list of critical materials are pretty much coinciding in most categories, and everything that is here in yellow is considered to be a critical material, which means its economic importance has increased, and there might be some problems associated with its availability in time. And as you could see here, nickel, natural graphite, lithium, cobalt, copper, they're all on the list of critical materials. And of course, these are things that that we use in batteries. I don't seem to be able to have a pointer, but hopefully you could see my my pointer here. Now, again, in materials extraction and refinement, for example, if we think of main anodes and cathodes for lithium-ion batteries, people categorize them very nice in terms of cost, safety, cycle life, power and density, and energy density. And these are easy metrics that we can put together for graphite, let's say for the titanates, lithium titanates, or also for the type of LMO, NCA, or NMC type of materials being 111, 811, or other type of NMC for LFP or for LCO. But what about sustainability? How can we add another line here that would reflect sustainability? And how can that be accurate? That would be nice when we talk a certain material, besides thinking of cost, safety, life cycle, power density, energy density, to think of sustainability as well. But that's a very difficult thing to do because of the complexity that I showed. And now, of course, we also have to think about the abundance of these elements. So, for example, lithium-ion battery versus other battery chemistry. So we have here lithium, copper, cobalt, nickel, manganese, graphite, and this is their abundance in the Earth's crust. And then we have here other elements, future battery chemistry from potassium to magnesium to sodium to calcium and aluminium. That's the abundance of these elements, and you would see that it is much higher, in particular for calcium or for aluminium, but all of them are way, way more abundant than lithium. So we need to think about diversifying the battery chemistry and moving away from lithium, but we also need to think of what active materials are we using to avoid the use of this critical but so key transition metals, cobalt, copper, nickel, manganese. So in terms of materials extraction, this graph here that we made show main countries involved in the mining of certain resources. And also at the bottom here, we put the one that own the reserve. So if we think of lithium, we think, of course, South America, Chile, Argentina, Australia. Cobalt, we think the Democratic Republic of Congo primarily, and some in Australia. If we think of graphite, we think mostly China, Brazil, Mozambique. Manganese, there's in South Africa, Australia, Gabon, Brazil. Most of the nickel used to come from Russia. That's why in 2023, nickel became on the list of critical materials because of the war. And so now people are looking a lot for nickel towards Indonesia. There's nickel in Philippines and a little bit in Australia. And copper is more abundant around Australia, US, China, Peru, Chile, and so on. We need to think also about evaluating the risk factors that could prevent the continuation of relying only on lithium-ion batteries, global warming potential, end of life and material waste, social and environmental impact of extraction, cost of extraction, scarcity, supply risk due to geopolitics. I just gave you the example of nickel, and in particular, the concentration of the supply and the concentration of war, because the more dilute the war is, the harder it is to mine the active material. Now, when I think manufacturing and distribution, this graph that I also took from this fantastic report from World Economic Forum days some years ago, but it's still relevant. If you look at the battery production, and this is only in terms of CO2 emission, which is something that is important to mention that is not the only factor. I've talked a lot about impact on the environment, and that needs to be considered, but it's easy to look at CO2 emissions in terms of sustainability. It's not the main factor, is an important one, but yeah, we need to keep in mind, and we need to look at other impacts on the environment. But anyway, this just looks at CO2 footprint, and you would see here that this is divided per raw material extraction, refining, cell manufacturing, use and end of life, and is divided by countries: China, EU, US, and the rest of the world. And you would see from this graph that the biggest impact on the environment in terms of CO2 emission is actually the manufacturing step. So taking all these materials and putting them together. Now, in a battery, we have different things. If we think of a lithium-ion battery, we have graphite, 22%. We have the cathodes, whatever that is. It's your choice of chemistry. Lithium cobalt oxide, NMCs, lithium nickel cobalt aluminum oxide, or recently there's a big drive for LFP. That's about 31%. Then we have current collectors, aluminum for the cathode, copper for the anode, for the graphite. We have an electrolyte, we have the separators, we have binders, we have additives. So there's a lot of complexity when we think about battery manufacturers and how do we select all these components, not only the active materials, but also the other things, so that they're sustainable. And I think in order to improve sustainability in manufacturing, we need to really manufacture so that we facilitate recycling. Moving on from the PVDF binder, which is quite toxic, cancerogenic, reprotoxic, to more biodegradable binders. Ideally, the current collectors are fine, but if we could somehow avoid them and make our materials into a freestanding conductive film somehow, we will increase the active material mass, we will increase the energy density, we will increase the volumetric energy density as well. So that'd be great. Avoiding critical materials, as I said. For making the materials, people keep using NMP. That's a very toxic solvent. We need to move away for aqueous formulations of the slurries. Standardize this formulation, digitally label our materials so we can recycle very well. And then if we think of pack, design for disassembling, avoiding glues, label components, and have easy locks so we can release the battery. That's how we can facilitate recycling. Now, in terms of manufacturing and distribution, as I showed you before, mining is mostly done from countries such as Chile, Australia, Indonesia, Congo, or South Africa. And then these materials are transported to be refined, and the cells being assembled mostly in Asia, which is China, South Korea, and Japan. And then these batteries, some stay there, but of course, a lot of us are shipped either to US and Europe, where we use them and we dispose them. So it's very complex supply chain, and it's not very clear yet who is responsible for what. Are the manufacturer responsible for mining? Are the manufacturer responsible for recycling? Or are the end user responsible for recycling? So we need better legislation here, which is, of course, happening, at least with the new EU directives. In terms of use phase, and I stole this from this fantastic review paper from Tarascon and Robert Domingo and all, I think in order to prolong use phase, we need to better understand degradation, and people have been doing quite a lot of fundamental research into this, and some significant progress has been made. And when we use batteries, it's of course a very complex system. We have a lot going on. We could have current collectors corrosion. We could also have the electrodes breaking up in small pieces, binder falling apart, electrical isolation. We can have on the anode in particular the dendrite growth and the SEI formation, which we need to control and understand so it keeps the electrode together and ionically conductive. talking about SEI, we can have a lot of crosstalk between the SEI happening on the cathode and the SEI happening on the anode, and things moving around between the two. And also we could have some heat generation when things degrade here. Gases are evolved, which lead to this heat generation, but also swelling and explosion of a battery, different electrolytes decomposing to different chemicals and causing all sorts of problems. Dissolution of the active materials themselves, forming HF. From the gas evolved, from the electrolyte decomposition, in particular when we use fluorinated electrolytes, but also this HF, we found out they can come from the PVDF binder as well. Cracks of the electrode, mechanical degrading, filling these cracks of electrolyte, creating shortcuts, changing the structure of the cathode, and so on. So this is a very complex mechanism. We still want the fundamental science here, in particular, as we move to novel battery chemistries. And of course, some of these novel battery chemistries are in the very early stage, so we can't even make them work properly. So it's a bit early to understand degradation. But for example, for other battery chemistry, as they are coming next to the market, such as sodium-ion battery, is very important to really try to do these studies and learn from all the huge knowledge in lithium-ion batteries and see what is different, because things are going to be different. And of course, to prolong the use phase, people are also moving towards self-healing binders, trying to fix the battery during operation, but also putting sensors in the battery so the sensor could tell you when something has cracked and whether the self-healing agent could fix this, or when your battery is about to fail. This is another very recent, more concentrated direction that the batteries have taken through the EU projects on the battery 2030. But again, these have been mostly focusing on lithium ions. And I think it's time to learn and apply this also to new battery chemistries. As I said, the second time around is very important. There's a very nice example. This is a very old example now of the Nissan Leaf batteries. They're powering the Amsterdam Arena, and we've seen a lot of new projects in this respect, where batteries that have been used in EVs are now taken out and used for stationary storage, where they're still good to go for significant number of years. And also recycling. Recycling is key, and that's the last part of a battery lifetime. And recycling is still pretty much a black box today. The significant research efforts, the significant companies are rising this space because we realize that actually our current batteries are reaching their first end of life, or maybe second end of life, and we really need to be better at giving a new life to these batteries. But the recycling of batteries today is still done a little bit like 18th century chemistry. You take the cells, you discharge them, you shred them in the small pieces, you try to get out the plastic and metals, leaching metals out, and you get this black mass. Electrolyte is not really recovered. And so we still have some pretty old school methods, which are pyrometallurgy, where you burn everything at high temperature, or hydrometallurgy, where you use a mixture of really nasty acids to recover these metals. We have somehow some greener methods being developed, but nothing on industrial scale, which is using ionic liquids or deep eutectic solvents, which are somehow slightly more environmentally friendly solvents that the acids, but also nobody has done a clear life cycle assessment on these technologies. Ionic liquids are very expensive, and also we have some bio based ways of recovering batteries, bacteria and plants. The question is, are they scalable? Will they ever be scalable? Is pretty much still in the research process. We're leaching, we're recovering mostly the metals and nothing much. very often lithium is not actually recovered, and only the very precious metals such as cobalt and nickel are recovering. There's a lot of development in direct recycling methods, where basically you get directly mixed electrodes and you lithiate them and you kind of recover the cathode. And this seems to be a much more promising direction to go in for the future. And I think we also need to get better at recycling and try to use better recycling plastics, AI and automation in recycling. This is also in pipeline. We need computer scientists to work together with robotics to create more advanced tools for disassembling these batteries rather than the shredding that is done today. Now, I've just given an overview of what I think has to do with sustainable batteries, but I also think that equally moving towards new battery chemistry is very important. And a while ago now, 2 years ago, in One Earth, we've been asked to write a perspective on diversifying batteries beyond lithium ion. So if you're interested, please read it. We've been given some timeline for commercialization of these different new battery chemistries as well. So as you see, we have been very optimistic with sodium, and we said less than 5 years. That was in 2022, and I still believe that we were right, and I still believe we will see sodium-ion batteries on the market, potentially in EVs and stationary storage this year. Potassium might emerge, but on a larger scale as a more high power type of battery alternative to lithium. We have all the multivalent batteries, aluminum, magnesium, zinc, which is pretty much developed in an aqueous phase, but can we do zinc in organics, calcium? And these are low TRL level. There's quite a lot of active fundamental research trying to make these batteries work. There's lots of challenges, in particular in finding the right electrolytes. They can reversibly plate these metals reversibly and enable a circular, a good life cycle of these batteries. But of course, there are equal challenges at the cathodes, where because of their high polarizability, not many materials can intercalate this. And then on the lithium side, we have new lithium battery chemistries as well. Lithium solid state, which I think it's a viable technology to improve the energy density of the current lithium ion batteries and improve their safety. And lithium sulfur, which probably, and lithium oxygen, in particular lithium sulfur, which are, I think, closer to commercialization. They'll be viable for some very niche application, in particular to do with drones and aviation. And of course, we have the opportunity to do dual ion battery configuration, where we can compromise in energy density but have a high power. So it's very important that we diversify beyond lithium while respecting still this principles of green batteries that I told you at the beginning, and we move towards a new battery chemistry. Myself, I've been doing a lot of research on sodium-ion batteries, in particular on anodes, but I don't think I have time to tell you about my research. I thought, since it's a plenary talk, it's nice to set the scene and give an overview. Sodium-ion batteries, as I said, I strongly believe we'll see them on the market this year. Together with my collaborators, Philip Alderher, Won-Young Sheng, who we wrote last year a 2-volume book on sodium-ion battery, which is quite timely. And there's quite a lot of companies there at various stages of development with sodium-ion batteries. I will mention Faradion, that started in the UK and now has been bought by Reliance in India. Tiamat in France, which they developed the sodium-ion battery-based screwdriver. It's very nice to see a product that is actually on the market powered by sodium-ion batteries. Of course, KATL, which keeps announcing that we will see that wonder sodium-ion battery, and hopefully we will see this year. The Haina Battery, who organized the Sodium-Ion Battery International Conference last year, and I had the pleasure to drive in this sodium-ion battery demonstrator. So yes, sodium-ion battery cars exist, and we've also visited their stationary storage facilities. And this is actually the closest I've seen myself personally, sodium-ion batteries being commercial, and there's Natron Energy in US, which is using sodium-ion battery for data storage or pulling this large things like aeroplanes around the airports. And they all have different chemistries in terms of cathodes, and you would see that they are all relying on these hard carbon anodes, which are quite difficult materials to study, and that's what we did. This is what my group did. We've been looking at how can we really fine-tune all the properties of this hard carbon so we can store a maximum amount of sodium. This is on graphite, so you see lithium goes happy in graphite, so does potassium. Sodium does not, and DFT says that it doesn't like it as well. There's very unfavorable interactions between sodium and hard carbons. And so, as I said, we're looking. Hard carbons are difficult. People believe the hard carbon is just one thing and you can take anything and burn it and you'll get a hard carbon. But in reality, maybe yes, that is true, but you really need to understand all these parameters, the interlayer spacing, the graphene layer extent, the average carbon bonds, the pore, whether they're closed and open, the crystallite sides and so on, at the defects, whether there are heteroatoms, hexagons, and pentagons, to really figure out the best hard carbon for sodium-ion batteries. So we've been doing these hard carbons from renewable resources using a mild hydrothermal synthesis for a while. And as I said, we've been testing this, and we've been doing this big study on the mechanism where we've looked at the effect of interlayer spacing, pore diameter, size. We've been using a lot of inoperando characterization, such as NMR to figure out the plateau, but also DFT calculation to figure the pores. And we came up with the fact that if you want to have an ideal hard carbon, you need to have the right interlayer spacing that allows sodium to go to your closed pores where sodium is plated as a metallic plating. And the plateau comes from the plating of the sodium, and the slope comes from mainly interaction of your sodium with the defects of this carbon, but some degree of intercalation. And by understanding all of this, you could fine-tune your materials to get the ideal material. Just to say that when we do batteries, it's very important to marry engineering and fundamental science, and also do a life cycle assessment on your materials to really understand that based on the way you prepare your material, you manufacture your electrodes, and not performance at a large scale, you are where you have to be within the environment. And that's what we do a lot for our materials as well. And we're comparing with other materials existing there. So for example, we look here at doing a hydrothermal carbonization versus a normal carbonization and the impact it has on the environment, not only on the global warming potential, but all the other categories as well. It's very important, if you can, to take these materials to real devices and pair it with the real cathode, test them in pouch cell, but also figure out where can you improve. But if you want your materials to go somewhere on the market economically, how do they compare in performance with other existing commercial materials? But in particular, what is their cost and how you could potentially optimize the cost of your materials? And that's kind of going all the way from fundamental science through impact assessment, through the real scale. The last thing I want to say, I'm already talked too much, is that all of this is very complicated, and I think that we make a lot of mistakes when we prepare these materials by hand. And so I really think the future for batteries is to try to automate them from the material synthesis to electrode preparation to assembling electrochemical testing, and then have this loop across all the life cycles where we can actually have reliable data, we can accelerate fundamental knowledge, we can have innovative fundamental science, and also reduce the gap between fundamental research and translation. And I think that is an important future for the batteries as well. So I'll finish by saying that you know, thinking about sustainability in battery is such a complex thing. This is my group, but the people that really contributed to what I showed you today are all these girls plus Johnny here in the middle. So I would like to thank them very much for their contribution, and thank you for your attention. And I'll stop sharing and move to the next speaker.
Thank you very much, Magda. That was a really nice overview of sustainable batteries